So my name is Gavin Roy. I'm the CTO at AWeber, and I'm going to give you a little talk about how we use Rabbit. If I can figure out how to change slides. There we go. So AWeber, we're an email service provider. Our mission is to deliver powerfully simple marketing software for small businesses that does 90% of the work for you. We've been using RabbitMQ at the core or the heart of our infrastructure, our application architecture for over 10 years. And a little bit about me. So I've been involved with RabbitMQ for some time. I've written numerous Python client library applications. I wrote the book RabbitMQ in Depth. And I also wrote the auto cluster functionality for RabbitMQ, or at least the original version of that. So our RabbitMQ application architecture, we think of probably very similar to many other implementations. We have a lot of different publishing applications. We have a lot of different consumer applications, and we have multiple RabbitMQ clusters that pass messages amongst each other. So we also have direct integration with Postgres. So in our Postgres database, we actually emit transactional information directly into Rabbit, which is pretty cool. And we classify our use of messages into three distinct areas. The first are events, and this is the primary use case for our usage of RabbitMQ. Events being something happened in our ecosystem. Could be anything from a customer logged in or used a particular feature of our software to an email message was sent, or one of their subscribers opened that message or clicked on it. This is the predominant use case for us. But we also use RPCs. Now, we tend to think of these RPCs a little one-sided, but it's, will you go do work for me? And then finally, transaction stream. And we use the transaction stream for microservice coordination to make sure that data is distributed and applied correctly across the various different application tiers. So our event messages you can think of as the neurons for a distributed application architecture. Our consumers are reacting to something that happened. So we have a lot of these different applications that are doing anything from recording information to a database to causing and triggering events within our workflow engine. And we have quite a number of these different events. 61 different high-level events, and all sorts of different purposes. Part of our thinking around this was, if we design for what we're doing now, but enable ourselves to react from the future, we don't know what workloads we're going to add into our system. So we can write our applications for what we need to do now, but think of it in a way where a particular event type might get used later, and we don't know what that purpose would be. It's been very successful for us in that as we went through this process, for example, as we designed our customer analytics system, we created events that said what happened with regard to a message, but then we were able to tie into that event stream and build a whole custom workflow engine that allowed for example tagging to subscribers when they interact with a message, or other similar things that we had no idea we would use when we originally created the event stream. We use topic exchanges pretty much exclusively, and we categorize our events on the types of messages that we're sending. So for example, we'll say these are subscriber-related events, account-related events, credit card processing events, that sort of thing. We use our messages in a way where we consider them to be idempotent. So while we're publishing them generally once, the way that we write our consumer applications, we expect that their operations are idempotent, so that if an event needs to be republished, for example, in the case of disaster recovery, the application behavior will not, for example, insert the same record twice, or perform the same counting event or function twice. And finally, this event stream has become the building block for our AI system. So because we're publishing all these events, we take all that data, we aggregate it, and we put it into AWS. And we've been building a data lake based upon this event stream. We have terabytes of data from this event stream coming through. We take the data, we use Kinesis Firehose, and we take that data with Kinesis Firehose and we turn it into Parquet files stored in S3. We use Athena to query that data. Next is our RPC style of messages. So one thing you'll notice in this slide, and probably a few others, is the weird artwork. I experimented with using DALL-E 2 for this slide deck, so you got some interesting results here. It's kind of fun. The RPC messages. So our RPC messages are responding, our consumer applications are responding when another application asks for work. So a good example of this is when our workflow engine says, send an email to this subscriber for this customer. We have an email consumer called Composer that goes and it pulls all the data together, builds the email, and publishes it to the SMTP server. They may publish an event. So in that case, our Composer consumer then publishes an event that says, I sent an email. Very simple. And then once that email goes into the email server, we're actually monitoring for things that happen there, and we'll publish events that say the email was delivered, or the email was rejected, or it's been temporarily deferred by the remote email server. In this case, we use direct exchanges. We don't expect multiple RPC consumers listening for the same request, so we're very targeted in how we deliver them. And in most cases, our publishers are not expecting the consumer to reply and said, I did the work. So it's not RPC in the traditional, hey, go compute this for me and give me the result. It's more directive in saying, hey, you go do this thing. And we expect that it will do the thing. And if there are any errors, it'll handle that error behavior and take care of it on its own. Next, we have our transactional message stream. So again, that's usually for microservice coordination. So for example, we have a tagging service, and our tagging service is really for tagging anything in our ecosystem, whether it's our customer subscribers, our customers' accounts, or various other objects within our system. And we transmit the transaction stream for that as a way to keep other databases, for example, an Elasticsearch search index, up to date with what's happening within that microservice without having to have that microservice know how to talk to Elasticsearch. We use topics for this, so we'll use a compound key where it would be the transaction stream name, and then appended with insert, update, delete, for example. So if you only want to see what data's been added, you can subscribe for just that, or if you want to see everything in a life cycle for a transaction, you can see that as well. And the data structure that we use for this is the same across everything, from our Postgres integration to our microservices that publish, and that is we carry in the body the data type, the transaction type, is it an insert, an update, or a delete, the timestamp of the transaction, the new record that was added, and the old record if it was updated or deleted. For the Postgres integration, we wrote a system called MQ, and that's available on GitHub. And it basically ties in using PGQ, which was a system that was developed for an old version of Postgres as a replication engine. The folks at Skype wrote this. It's a really cool system. But basically, it creates in Postgres queues to do guaranteed ordering for replication. We leverage that and lean on that heavily and basically take those messages as they go into PGQ and publish them over AMQP. It uses JSON serialization of that transactional data. And so it's one of the few exceptions in our ecosystem where we are transmitting JSON, but we know exactly what the structure is going to be. Now, I say it's one of the only that we use in our ecosystem because everything else is published using Apache Avro datums. So Avro, like other binary RPCs, Thrift, gRPC, it's a strongly typed contract-based binary data encoding system. It can be used as an RPC protocol. We're just using datums on the wire. It also could be used to collect multiple records, similar to Apache Parquet. But the way that we use it is we have our Avro-based schemas, and we have a schema registry. And our publishers and consumers go to that schema registry and say, I know I need to publish this type of message, or I need to consume that type of message. Give me the schema for it. And then it will encode that schema as an Avro datum and publish it on the wire. And what that looks like is, when you're in the RabbitMQ UI, this. A bunch of gibberish. It's actually base 64 encoded binary data in the message payload. But we take care of passing the schema that we're using in the AMQP message property of type. And that's basically the key that's used to go grab it from the appropriate place to use for encoding or decoding. We also have a consumer that we use called Transmogrifier. And this consumer is somewhat helpful for us in using this strongly typed system for when we need to create new revisions of schemas for applications. So I mentioned that we emit an event when we spool an email into the email server from our Composer application. Different consumers downstream are listening to that event, but one of the things that I can't guarantee as CTO is that all of my product teams can update their consumers to prevent, in time, that would prevent new versions of a schema from being published. So what Transmogrifier does is it allows us to take, for example, a v5 of a schema for a datum that's being published, and then transform that message body to v4 so that the consumers that are not yet compatible with the v5 message can still consume the v4 version. It's a pretty simple application, but basically it just has transformation rules that say take these body pieces, transform them however you need to transform them, and then republish it as this other version. We also use it as a way to bridge those JSON events that I mentioned, for example, with the Postgres side of things, and turn them into Avro-encoded events. Now, I keep talking about the Avro-encoded events. One of the things that it has that as a benefit is because it's defined with a schema, but then packed binary data, we're not transmitting all of the information about what the rows are. For example, when you have JSON, it's a key value document, right? So you're transmitting a lot of extra data that you may need to compress. By using Avro, we're basically only transmitting the data and have an explicit contract as to how to decode the data. I've talked a lot about consuming. We use a consumer framework, which I talked in detail about last year at the RabbitMQ Summit. It is a Python-based consumer framework that allows us to write applications for consuming messages that behave in a reliable way, that have supervision, that have a standard contract for how to deal with problems with a message versus operational problems in the environment. And it's batteries included, so everything from auto-instrumentation, tying into Sentry, profiling, all that sort of stuff is built in. And it also allows for, based on the consumer class, auto deserialization. So when somebody's actually writing a consumer application, they don't think about the Avro. They don't think about going to the schema repository and pulling it down. They just write their consumer application. They set the class attribute that says what type of messages they support, and they move on from there. So moving on from application architecture into operational management, I'm going to talk about how we set up and manage our RabbitMQ clusters, how we monitor them, and that sort of thing. So the first aspect of this is configuration management. How do we go from no infrastructure at all to having a cluster deployed, configured, and managed? So we focus on three different aspects of that, right? There's the how do we install or upgrade Rabbit? How do we configure the rabbitmq.conf or advanced.config file or TLS, things like that? How do we tell the cluster, the individual nodes that they're part of a cluster? And how do we handle runtime configuration? That is the aspects of the broker that applications expect to use, whether that's users, exchanges, queues, bindings, etc. So for broker management, we use Ansible. And we have an Ansible role that we developed in-house and plays for the various clusters that we have. And we use rundeck to execute upon that. And so for an individual cluster, we might say, you're on a specific version of Erlang, you're on a specific version of RabbitMQ, and here are all the parts of the ecosystem that we deploy as part of that. RabbitMQ, Erlang version, Telegraph, which we use for our monitoring, our SSL certificates for AMQPS and HTTPS, and making sure that the tuning that we need to do at the cluster level is performed correctly. We use HashiCorp console pretty extensively within our infrastructure as it is for our service discovery layer as well as our service configuration. So it made a lot of sense for us to use that for RabbitMQ as well. And that's actually what led to the development of RabbitMQ auto clustering, was how do we add nodes within console and then use console as a way to tell RabbitMQ about the nodes that are available in the cluster for itself. So we use the peer discovery console plugin. And then we also announce the RabbitMQ cluster as AMQP, AMQPS, and HTTPS within our console service. So we're not talking about managing DNS, for example, manually. We basically know we go to cluster name.service.environment.console for whatever it is that we're doing. If you were here for the previous talk, there was lots of really good information about rolling upgrades. I probably should have read the schedule before writing this slide, but I'll tell you a little bit about what we do. It's very similar to the process that was spoken about previously. We run our Ansible play serially, and that goes through node by node and actually performs nearly all the steps that were detailed in the previous talk. We also hide the node, in addition to the RabbitMQ maintenance, we hide the node with console maintenance, so that way any new clients are connecting, they bypass the node that's in maintenance before ever doing anything else. The client behavior is important. So one of the aspects of rolling upgrades that is critical is that if your client is disconnected from the cluster because of maintenance mode or the node going down, it needs to successfully connect correctly. And so that was one of the key things that, for example, having that framework for our consumer applications and having a framework for our publishing applications was really important as far as making sure that as we go through and do our rolling upgrades, our applications continue to operate without any issues. As you can see, Dolly here took the idea of rebuilding a train on the tracks and gave you that awesome image. So next is our runtime configuration. And we really think about how we manage this is more about disaster recovery than it is about automation in management of our configuration. So I encourage our team actually to think through the topologies and manage the topologies manually. We have a bidirectional git sync-based approach, so we have a repository that contains the RabbitMQ definitions for each cluster. And we have a workflow by which stuff gets added in. And Git basically is responsible for, or we have an application called RMQ definitions that's available on GitHub that takes the JSON-based file and applies them to RabbitMQ. And the nice thing about using that compared to just exporting the data out of Rabbit is it's deterministic, which is really important for using config management in a Git-based approach. Next is monitoring and how we think about monitoring. So there's monitoring for the purpose of alerts, creating dashboards that show the operational status, and also used for trending and analysis. So for that, we use Telegraph, and we use that to collect runtime stats. Really close to looking at how we could leverage Prometheus, now that that's a bigger part of our ecosystem, into this process. But as of right now, we're using Telegraph to collect that information, and we submit it into Graphite. And then we use Grafana for dashboarding on that. And then we use Sensu running on a local node to collect runtime state for that node and alert us when there are issues, broker not running, it's got back pressure due to memory issues, high CPU, that sort of thing. For user management, that is the authentication and authorization of our applications, we use LDAP internally for our users. That is my engineering team. Their LDAP credentials are what are used to authenticate into the management UI in essence and give them permissions to what they're allowed to have permissions for. And then we use the internal database for our applications themselves. So we're registering users for the applications and taking a very cluster-specific view at that part of what we do. Our wished future state is to integrate with HashiCorp Vault for the least credential aspect of things, so that we can have Vault say, here are the credentials that you're going to use. It goes out to Rabbit, creates those credentials, but then handles the life cycle of those credentials so that they're not long-lived. Again, I wonder, a great DALL-E masterpiece there. Finally, I want to talk about our best practices, the things that have been very useful for us and operating at scale in our message throughput. And really, these are our opinions, right? More than how we do the things we do, the opinions that have helped us be successful about what we do. First is we write simple consumers. Where at all possible, the consumer application itself is super simplified. So it's better to have one simple or 5 simple consumers consuming the same message 5 times than to have one complex consumer that's doing 5 different operations. It creates more robust workflows. We let Rabbit and the process of interacting with the message in AMQP help be deterministic about what we do in failures to create a more robust architecture. Right? If you have one consumer that's doing 5 different things and it fails on number 3, what do you do? So having 5 consumers performing their own operations independently means that when that 3rd thing fails, the failure mode for that is isolated. That makes it a lot easier to debug as well. Right? If you had one application consuming that message and it's doing 5 different things, you have to jump through a lot more hoops to figure out exactly where the failure is and how to address it. Whereas when I have this one consumer that's failing, it's easier to identify in Sentry what's going on. It's easier to identify in the code base what's going on. And so that's probably the biggest mantra, and one of the things that's hardest to really digest as a developer, especially if you're being told, okay, you've got this message. It does 5 different things. You need to write it to the database. You need to send out an invoice. You need to do all these other things. The natural inclination is, well, let me write the program to do that, as opposed to let me have 5 different consumer applications and 5 different Git repos, for example, to do that. The next opinion is around queue naming. So oftentimes you'll see whether you're using the default built-in queue naming or you're using an automated system to name your queues, and it's using random queues. Queue names can be deceptive, or at least very obscure, especially when you're the on-call response team trying to figure out why this queue that normally has high throughput and now is developed a million message backlog. You know, what is this application? Who does it belong to? How do I get it fixed? And so we try and name our queues in a way that makes it both clear in intent on who owns the queue from an application perspective and what its purpose is. So it's not just my application, it's my application that writes to the database. And that makes it very helpful in figuring out, during operational issues, who do I talk to? How do I make sure that it gets fixed? Seems simple, but left to their own devices, with a large team, you end up with all sorts of different variations on queue names that can make it difficult to handle from a support perspective. Next is, how do we handle high throughput? One of the things that we talked about in our queue naming is the fact that we're naming it for applications, but we didn't talk about what do you do when you've got a queue with, or a publisher that's publishing, let's say, 10,000 messages a second, but consumers that as individuals can only consume, let's say, 100 a second. Well, obviously you would add a bunch of consumers, but the more consumers you add to a queue, you end up from a tuning perspective actually having some inverse behavior. There's diminishing returns from a internal management and Rabbit perspective by adding tons and tons of consumers to a single queue. And so what we do is we shard the queue. And we started this process by using the consistent hash exchange. So we're like, okay, well, we publish with a message ID, and that's something that we can easily hash on. So let's use the consistent hash exchange. Let's create a bunch of sharded queues, and we'll bind that exchange to the event exchange, and we'll put the consumers on it. And what we ran into is under load that created extra CPU utilization because it's performing the hashing operation on the property of every message that it's doing. So where we landed was using the random exchange. And even though it's the random exchange, we found that under load, it actually performs really well in providing great distribution that's pretty much even across all the queues that are bound to it. And the nice side effect of that is it uses very little CPU. So all of our CPU utilization is generally done in managing the message throughput on the individual queues. I talked about application behaviors and how when we encounter errors, we want to make sure that our applications behave well. The way that we manage that in a global way, so we started out the process by saying, this application over here has its own exchange for errors, its own queue for errors, and we used this pattern of message TTLs with a DLX to get the message back into the original queue for it to be processed again. And that didn't scale very well. That led us with a whole bunch of exchanges and a whole bunch of queues that it became difficult to manage. So where we landed was a standard pattern with a standard set of queues for errors, because errors tend to be pretty low throughput. We basically, in our consumer framework, publish a new header when there's an error where we say this was originally consumed from this specific queue. That message gets republished to a retry queue or a retry exchange, and based upon the bindings that are done, it makes its way into one of a set of standard retry queues. And those queues are named for the duration that the message is supposed to sit in them. Everything from a 5-second queue, a 30-second queue, a 1-hour queue, a 1-day queue. And then when the message TTL expires, RabbitMQ will automatically publish it to the dead letter exchange. And for that, we're using a headers exchange. And everything that is bound to that exchange is bound to the X original queue header property, so it makes it back into the queue where the error originated from, and conceptually the same consumer or the same consumer application. One of the more difficult things to get to come to terms with, I should say, from a monitoring and application behavior perspective was learning the lessons about being on call and not wanting to be woken up at 1 in the morning to not do anything when the queue depth for a particular queue is larger than the configured threshold is. So if we're always trying to keep our queues at 0 from a throughput perspective, it's very tempting from a developer perspective to say, okay, alert me when I've got 1,000 messages in the queue. But with a distributed workload and a non-deterministic amount of messages going through the system, what happens when somebody does something at 1 in the morning that is perfectly normal, but all of a sudden creates a higher than normal demand on your cluster? You don't want to be woken up for that, and that's a hard lesson to learn when it's not a problem. So queue depth is great for keeping track of when your application is not keeping up, but it is not the sole deterministic factor of there being a problem. And for that, we like to look at the ACK rate in combination with the queue depth. So if we know that there is a history of the consumer being able to ACK messages at 100 messages a second, but there was a publisher that was publishing thousands of messages a second, we know it's eventually going to catch up when that publishing diminishes, And so we like to look at the ACK rate and say, okay, is the ACK rate substantially different than it has been in the past? Is it at 0? And combine those things together for what we get paged on instead of just, there's 1,000 messages in the queue. One of the other interesting side effects of 1,000 messages in the queue is what happens over the course of, let's say, 10 minutes when you have publishers that publish quickly, then diminish, then publish quickly and diminish. You get flapping, and you get an alert. PagerDuty says, hey, wake up. You wake up, you go to your computer, and the alert's cleared. You go back to bed, it alerts. You get to your computer, it's cleared. So ACK rate is really important from our perspective in taking that into account when we are creating alerts based upon our workload. I mentioned previously using the type property. These are the primary properties that we use in our AMQP messages. We want to know what application is publishing it, but not just what application, but what version of the application. Because we may have multiple versions of an application running in the ecosystem. We're going to want to be able to tie back, especially if we're trying to troubleshoot some sort of issue, where exactly it came from. We also use correlation ID as a tracing mechanism across our entire ecosystem. So for example, when an HTTP request comes in, we assign a correlation ID, and everything that happens after that gets passed all the way through our system, including our AMQP messages. It's really handy to go to our log aggregation system with a UUID that represents a unit of work that spanned multiple microservices and multiple AMQP messages to figure out what happened in what order. We uniquely generate a message ID for every message published, and that's just a handy, let me go into our data warehouse, for example, if we need to, and actually see the original source of this, or where it may have come from. We treat timestamp in the AMQP property different than the way that we might think about the timestamp in an event. So when we're publishing an event, we always include a timestamp that is when the thing happened, independent of the message. And the timestamp in the AMQP property is the timestamp of when the message was published. And so that way, we're separating the content and the time around the thing in the content from the AMQP message itself. Again, just a useful way to differentiate and have some information. We actually use this also in our alerting to say, when did a message enter our system? We could say, we've seen this message spinning through our retry queues for this amount of duration by having that timestamp set. And finally, the type, identifying what schema we're going to use, the format and data in a message. I mentioned spinning messages. One other aspect of that we use is we have automated shutdown of consumers. So there are multiple problems that could happen in a consumer. If you think about developing for the cloud, I may have resources that have been taken away from me. So Amazon actually yesterday decided that they were going to update all of our Postgres 14.2 instances in RDS to 14.3, which we told them it was perfectly okay to do. But what happens when we have a bunch of consumers writing at high velocity to RDS is they all disconnect and they raise internally what's called a processing exception that goes through our retry queue. Well, what happens if instead of it being a less than a minute downtime, it moves into a 60-minute downtime or 120-minute downtime, and we have it on a 5-second delay for retry? That means that we'd have that consumer spinning over those messages over an extended period of time. So we have an emergency brake that's built in that instead of wasting the compute on retrying over and over again due to an operational error, it'll actually shut the consumer down, because maybe it's a problem with the consumer and the configuration it has. Maybe for some reason, that Docker image running in Kubernetes has a stuck DNS resolution at a host that doesn't exist anymore. And so the framework says, after 500 tries, shut down because something's obviously wrong that shouldn't be happening. The other side of that is we have this is a bad message. We've been trying this over and over and over again, and something about it's wrong, so we're going to drop it after a certain threshold. That's really useful on that whole spinning message thing. Maybe a bad publishing application put in a null ID in a place that the schema said was okay, but in the end really wasn't. So that's all I have. Again, my book is RabbitMQ in depth. It's a little dated at this point in time, but I still feel fundamentally covers a lot of important questions about running a RabbitMQ cluster. I'm on Twitter. I announce all my new software updates and fun stuff there, and I'm also on GitHub.
Thank you, Gavin. So do we have any questions here in the room?
Hello. So I was interested in your Transmogrifier and wanted to see if I could get a couple details about that. So yeah, it's transformation rules. And this is because like my team owns a sort of at least high-level similar sort of thing. So how does it work? Like what sort of frameworks do you use? What, you know, how does it actually run the transformations?
Sure. So in essence, it is a set of rules that we manage in console that apply to a particular message type. So when the message comes in, we're looking and saying, okay, we see this is a foo v5, and we need to publish a foo v4. And then there's a set of rules that apply to it at a field level. So we'll say, drop this particular attribute or add this attribute with this type of value computed based upon something or null or whatever it may be. It's got the ability to tie in to make HTTP requests to services to resolve information, basically using URI formatted strings. It's something that I actually intend to open source at some point in the near future as soon as we're able to pull out some of the internal system aspects of it. It uses the rejected framework, and that configuration for those mappings are tied to attributes at the consumer level configuration. But we use console very heavily, and we manage all that configuration in console. So it makes it really easy for us to add those transformation rules on the fly.
Thank you. One question from the online audience is there any reason why you are not using Prometheus?
Because a lot of our infrastructure predates our operational use of Prometheus. So our Prometheus usage has primarily been tied to Kubernetes specifically, and we don't run RabbitMQ in Prometheus, or I'm sorry, in Kubernetes. And so because we're primarily on VMs, and we didn't expose Prometheus outside of our Kubernetes clusters. Now that we've gotten into the practice of doing that, we are looking at moving that. And I'll also say a lot of the work that we've done as far as managing these clusters predate the Prometheus exporter in Rabbit.
Thank you, thank you. Any other questions?
I just build on top of what you said. Are there any plans to move to Kubernetes with the entire RabbitMQ setup? And in case you're going to do that, you're going to drop all the Ansible scripts and use the operator?
I would probably move to AWS's hosted RabbitMQ before I run it in my own Kubernetes cluster.
Okay, thank you.
Thank you.
Thanks, Gavin. Nice presentation. It was quite
Thank
a lot. I'm still trying to digest stuff on back of my mind. So on user management, you mentioned that you're storing credentials in database. So how do you do it? Are you using some sort of plugin?
We actually, no, the internal database within RabbitMQ. So we go into the admin UI, we say we're adding this new application with this password, here's what it has permission to use. And then we rely on our Git integration to keep that backed up.
Ah, all right.
Thank you. Anyone else? Oh, yeah.
I've got another one. So I noticed that you use rolling upgrades to upgrade your brokers. Have you ever encountered the situation where you have to downgrade? And does the rolling upgrade work okay for you in that case, if you do?
Well, I haven't had to downgrade, but I have run into an issue where as part of our upgrade, we had to manually intervene. And in that process, part of our process is to expect So we're able to live with more constraints than a hosted service would have. Our expectation is generally when we're going into an upgrade, we're in a good operational state where our general directive is our queues are as close to near zero as possible in queue depth. And we take a backup of varlib amnesia or varlib RabbitMQ to make sure that if we need to roll back, we can.
Thank you. So I think maybe one last question, if anyone has one. Okay, I have one. You mentioned at the beginning it's important that you are not reapplying the same message, right? So idempotency is important. So what are the strategies you are doing to avoid that?
I mean, it really depends on the application itself, but usually it ties into the behaviors both in HTTP APIs. So we rely heavily, similarly, on AMQP properties. We rely on the HTTP protocol. We're going to be checking for conflicts in the application and returning a 409 status code back to a consumer saying you tried to do something that you shouldn't have been trying to do, or within the database layer itself and ensuring that the work that it's doing is idempotent, relying on well-architected schemas and contracts with the database.
Thank you. So if we don't have any more questions, then I think that's it. Please give a big applause for Gavin.
Thank you.